The gummy baryons discovered the ABCs of radioactivity, only they've been called alpha, beta, and gamma since 1899 when Ernest Rutherford named them. In Part 1, we learned that alpha and beta rays are really charged particles. In Part 2, we'll learn that neutral gamma rays are really photons, and like all photons, gamma rays can travel as electromagnetic waves. Now let's turn our attention to gamma rays and learn the difference between visible photons, virtual photons, and the nuclear photons that make up gamma ray radioactivity. Visible light rays are usually photons produced by orbital electrons. Remember those photons that the orbital electrons are exchanging when they get close enough to the nucleus? The EM force stretches an orbital electron into a standing wave by turning the electron into a photon and another electron. The photons exchanged with the nucleus are called virtual photons, and this type of binding by the electrical force is known as the electromagnetic or EM force, and it can couple energy into standing waves, and standing waves can store energy. Standing waves are actually all around us. A standing wave is like the energy oscillations a guitar string makes when it's vibrating at resonance for one tone. And it will resonate for a long time because the pluck energy is stored in the standing wave and is not being directly released. Another example of a standing wave storing energy is the Tacoma Narrows Bridge in Washington State. It was designed too thin for its length and acted like a guitar string. Every gust of wind added energy to the wave motion, and none of the previous energy was damped out. The oscillations of the bridge got larger and larger until it did the wave one last time and oscillated itself into pieces. In contrast, gamma rays are much higher energy invisible photons that are emitted by the nucleus, not from orbital electrons, not from orbital standing waves.
The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny thread. There it goes!
Usually, an orbital electron just exchanges photons with the nucleus and no energy is lost from the atomic standing wave, and no orbit decay occurs. But sometimes a photon separates from an orbital electron and doesn't exchange with the nucleus. In the case of a laser diode or laser pointer, we see the photon leave atomic orbit as a flash of light, and a lot of flashes add up to a beam of laser light. But this light energy that comes out of the atom is really energy that has been removed from the standing wave. The result is that the orbital electron reappears or decays into a lower orbit at one end of a new, smaller standing wave, one with less energy in it. Electricity going into the laser diode supplies energy to pump the orbital electron back up to a higher orbit, and the process is repeated over and over again. Occasionally, a photon escapes from the nucleus instead of the standing wave. It doesn't exchange with an orbital electron, but just keeps on going. This nuclear photon is called a gamma ray. It is one of Rutherford's 3 types of radiation, the one that travels the farthest through matter. Recall that Rutherford stopped gamma rays with a 1/4-inch piece of lead. The energy for gamma radiation doesn't come from the orbital electron standing wave. It comes from shape changes in the nucleus that usually happen after an event like alpha decay. Physicists have shown that gamma rays should also be present if cold fusion ever happens, and so far no one has measured any cold fusion gamma rays. But for alpha and beta radiation, the nucleus is the source of energy in a different way than gamma rays. Because alpha and beta radiation consists of mass particles, they can carry off enormous amounts of energies in the form of kinetic energy. And the source for this kinetic energy is matter converted to energy in the nucleus. The energy just comes from Einstein's famous equation, E equals mc squared. Notice that in Einstein's equation, c is just a constant. It doesn't mean that matter has to be moving at the speed of light to convert it to energy. It just means that if you weigh some matter, then you know how much energy it can be converted into by simply multiplying it by the constant c squared. So the energy for alpha, beta, and gamma radiation all starts in the nucleus, and that's the basic requirement in order for an atom to be radioactive. Isaac Newton is the person that figured out that any object in a circular orbit is undergoing acceleration because it's not moving in a straight line. Since objects in motion tend to stay in motion, he reasoned that a force must be deflecting the planets from the straight and narrow, and force always brings acceleration. Newton knew that the moon and planets had to be acted on by the force of gravity because they didn't travel in straight lines per his laws of motion. Likewise, if an electron orbited around the nucleus, it would be undergoing constant acceleration. And when a negatively charged electron undergoes acceleration or deacceleration, it loses energy, like at a cell phone antenna that's transmitting. So orbital electrons can't circulate in atomic orbits because the resulting acceleration would cause energy loss, and that, in turn, would cause the electron orbit to decay into the nucleus. Is the same thing true for neutral photons of light? No. Photons don't lose energy when they slow down or deaccelerate. We see this all around us. Light bends or refracts when it enters the glass of a prism, or when it enters the water in a swimming pool, or raindrops in a rainbow. The key is that photons travel at the speed of light, or c, only in a near vacuum such as air. But photons slow down when going from air to glass or air to water. And, surprisingly, they speed back up to velocity c when going back from water to air or glass to air. This is possible because they are neutral and don't lose energy during acceleration. To understand refraction of light, think of a photon as a car sliding on a patch of ice. The photon wavefront is like the front axle of the car. As shown in the figure, the right front tire will reach dry pavement first, and as it slows the vehicle down, the car will turn to the right. So the left tire will be going faster than the right tire until it too reaches dry pavement. And the amount of turning or bending will depend on the color or energy of the photon. Because a blue photon has more energy than a red photon, it will bend more when it strikes the air and water interface. Think of the blue photon as a car with wider tires. The right front tire will grab better and turn the vehicle more than the thin tires on a red photon. Quantum mechanics and the wave equation finally explained why there is no orbit decay. The standing wave formed by photon exchange between an orbital electron and the nucleus can store enough standing wave energy to keep the electron at arm's length. As a simple analogy, compare the photon in a standing wave to a swing that the orbital electron and the nucleus are oscillating or pushing back and forth. If you've ever tried to move in too close to a swing in motion and push at the wrong time, you know that you get pushed back with all the energy stored in the swing system. But at just the right distance, the electron gets the opportunity for a free ride, meaning no energy loss, to the nucleus on the photon swing. However, because this ride has been hitched on an energy storage mechanism, the photon gets swung back out of the nucleus with as much force as it swung in on. The more technical way to explain this lack of orbital decay is the Heisenberg uncertainty principle. If you ever become a physics student in college, you'll probably get the chance to derive Heisenberg's uncertainty principle for a standing wave. The uncertainty principle equation tells us that we can't simultaneously know both the position and the velocity of a particle of matter, an orbital electron in this case. But because we do know the orbital electron is moving at the speed of light due to photon exchange, it's strictly the position we can't know in the case of the orbital electron. Thus, for a volume smaller than 1 photon wavelength, the photon and subsequently the electron must go everywhere in the standing wave. The orbital electron can't be pulled into a single location at the center of the atom. The uncertainty principle sounds like more quantum mechanic magic, but we can see it in action with our own eyes. If a closing slit is placed between a laser pointer and a wall, the red image of the spot on the wall will get smaller and dimmer until something strange happens. Here's a hint. We know the velocity of the light, and the slit is trying to define the position of the photon. What will happen is that as the slit narrows to the wavelength of the laser light, the red dot on the wall will start to get wider instead of smaller. Once both photon velocity and position are constrained, the photons of light will start being located everywhere, just like the orbital electron. Outside the atom, this being everywhere effect is called the diffraction of light, because it is caused by the same subatomic uncertainty principle that keeps orbital electrons from parking in the nucleus or having decaying orbits. Clicking on the movie at left will show the slit being closed as the red spot grows slightly wider. In the still pictures at right, the room lights were turned out to enhance the visibility of the laser spot diffraction pattern. To see this effect, you need a laser pointer and a couple razor blades that you can move closer together. And when you do that, you can see that the spot actually gets bigger. We have learned that the orbital electrons don't actually orbit the nucleus like satellites. We have also learned that orbital electrons are bound to the nucleus by a photon exchange. And we have learned that orbital electrons can't park in the nucleus because of the uncertainty principle. Finally, because the photon is neutral when it exchanges with the nucleus, the orbital electrons exhibit one additional unusual behavior. The exchanged photon can leave the nucleus at any random angle, again because it's neutral. This gives the orbital electron the appearance of hopping randomly in its orbital shell. So because the orbital electron can really be anywhere from one moment to the next, its location is often described as an electron cloud. And though the photon hop from nucleus to orbit has a random angle, the radius of the hop is constrained to just a few distances that support wave continuity. This means that in order for the photon or light packet to participate in a standing wave trip in and out of the nucleus, the wave must go far enough so the wave ends meet in 3D space. Peaks must meet peaks, or valleys must meet valleys. Plus, the wave ends must not just meet on the trip in and out, but on any side-to-side trip too. As shown on the slide, in the case of an orbit that supports 4 side-to-side wave cycles or wavelengths, the next allowable orbit distance must support 5 side-to-side wave cycles or wavelengths to ensure wave continuity. So orbital electrons are allowed to occur only at orbits with discrete steps. These steps are better known as orbital shells. In part 1, we learned that alpha and beta rays are actually particles. As a result, examples of the strong and weak force were given. But in part 2, we have learned that gamma rays are actually invisible, high-energy photons of light. So now we need to review examples of the electromagnetic force, because that's the force that governs photons. The electromagnetic force, or EM force, was once 2 separate forces that were known as the electrostatic force and the magnetic force. Some students may know that it was Maxwell's equations that combined these 2 components. And most people know about magnetism, but what is the electrostatic force? Well, when you rub a balloon on your hair and then stick it to the wall, that's the electrostatic force in action. It's just the way the electrical force behaves when only a few out-of-balance electrons are involved. Clearly, it's not enough force to lift the Earth. When the balloon gets close to the wall, its excess, out-of-balance negative charge will actually repel any loosely bound wall electrons deeper into the wall. And it will also repel the negative side of some molecules away from the balloon. This brings the positive side of those same wall molecules toward the balloon, so the surface of the wall actually starts getting out of balance positive and thus reinforces the attraction of the balloon. But how do electrons get loosely bound in the first place? As depicted on the slide, electrons become loosely bound when enough inner orbital electrons create enough negative charge to partially repel the outer orbital electrons. The electrostatic force that pulls the balloon to the wall is the same force that pulls electrons through a wire. When we increase the voltage and therefore the force, the electrons can be pulled a longer distance. It takes at least 25,000 volts to pull an electron through an inch of air, and we see this as a spark. If we want a spark to be twice as long, the voltage needs to be doubled. How long a spark do you think we can make with a 1.5 volt battery? For a voltage that small, basically the wires have to touch in a make and break contact motion because the spark length is so short. And the spark length doesn't depend on whether the battery is C, D, or AA. The spark length will be the same for all batteries with the same voltage. If you could buy 25,000 volt batteries at any store, the bigger sizes would just keep the 1-inch spark going longer because they would take longer to drain. Electrostatic force and magnetic force are really the same thing. Which one we see depends on our relative motion with respect to the electron being observed. Once voltage gets free electrons moving, a magnetic field forms around them. This happens to the sparks going through the air or in a wire carrying electrons, because when electrons move past us, we always see a magnetic field. For example, suppose an electron-charged balloon were taped on the moving walkway at the airport. We would indeed see a very small, newly created magnetic field when the stack of electrons on the balloon zoomed by, kind of like a really slow spark. The important thing to notice is that the electrostatic force turns into a magnetic force once motion is added to our point of reference. And it doesn't matter if we move or the electrons move. So suppose instead we taped the balloon to the floor and then we got on the moving walkway and zoomed past the stationary pile of electrons on the balloon. The relative motion is the same, so we'd still see a magnetic field. When we stand next to the balloon taped to the floor, we see an electrostatic field, but when we zoom by the balloon or it zooms by us, we see a magnetic field. Since it's the same electrons and the same field or force, we must conclude that the magnetic force is really just the electrostatic force with some relative motion occurring. That's why they're combined and described as the electromagnetic force. James Maxwell showed mathematically that the magnetic force and the electrostatic force were the same thing back in 1873, when everyone thought that the universe had only 3 dimensions. In 1915, Einstein showed that the universe had 4 or more dimensions. In his theory of general relativity, gravity rippled through the first 4 dimensions of space and time. In 1919, a mathematician by the name of Kaluza corresponded with Einstein and showed that adding a 5th dimension resulted in extra equations that matched Maxwell's equations. We know today, from something called string theory, that there are in fact 11 dimensions of space and that the EM force ripples through the higher dimensions, above 4. But what is this string theory, and why isn't it called Kaluza theory, and what happened to the Standard Model? Well, the Standard Model is still the best predictive model we have, but it's known to need some theoretical band-aids. For instance, fundamental particles shouldn't really go around changing from down quarks to up quarks. They should remain what they are. And when everything is based on point particles and their associated standing waves, it's difficult to account for structure. The Standard Model is not very good at explaining why a water molecule has an angle of 105 degrees between the hydrogen atoms when theoretically that angle should be 90 degrees. And the Standard Model hasn't been able to mathematically incorporate gravity. Gravity is just usually referenced with the Standard Model to summarize all the known fundamental forces. Fortunately, the string theory model addresses some of these limitations, but it's not very good at predictions yet. String theory shows mathematically that while gravitational force distorts and ripples through the first 4 dimensions of space and time, electrical force distorts and ripples through the next 6 curled up dimensions. The next slide will show computer graphics of these curled up subspace dimensions. As to why it's called string theory, well, Kaluza's 5-dimensional equations had some problems that didn't get resolved until 11 dimensions were considered. It turns out that the gummy models need string theory to actually be workable instructive models. When quark electrons hop and reform in a new go-to zone, they do so by exchanging neutral gluon particles. During that neutral transition time, the 3 charged up quarks could move slightly away from each other due to mutual repulsion. And then they would be drawn back together again by the quark-electron reformation. But this would cause a start and stop oscillation motion, and any start-stop motion applies acceleration. And once again, we have the problem of accelerating charged particles losing energy, no perpetual oscillator. The gummy models were originally developed from just the standard model concept of point charges, and this energy loss was a puzzling inconsistency in the models. Fortunately, string theory solves this dilemma. It allows quarks to vibrate in place without losing energy, like oscillating loops of a rubber band. This is exactly the kind of motion that the up quarks in the gummy models require. If the smallest building blocks of matter, or quarks, look like vibrating rubber bands, what does space look like at the smallest level? Well, according to string theory, space has 11 dimensions and sort of looks like the middle figure at right. And each of the 11 dimensions maps to a force or vibrational mode for the string. Gravitational force ripples through the first 4 dimensions of x, y, z, and time. The next 6 dimensions, dimensions 5 through 10, are curled back on themselves in something called Calabi-Yau space, as shown at the figure at lower right, that is adapted from the elegant universe. The electrical force ripples through these next 6 dimensions, including the weak, strong, and EM forces. The 11th dimension ties the others together by adding what has been described as a ribbon shape to the strings. So as we come to the end of part 2, let's review what we've learned. Rutherford identified 3 kinds of radioactive rays being emitted by uranium ore: alpha, beta, and gamma. In part 1, we learned that alpha and beta rays are really charged particles ejected from the nucleus. In part 2, we learned that gamma rays are different. They are neutral massless photons that are released by the nucleus when protons and neutrons are rearranged. And this rearrangement often occurs after alpha decay. Gamma rays are high-energy photons, and like photons of visible light, they can travel as electromagnetic radiation, but they also penetrate matter, like X-rays. In part 1, we learned about 4 forces that became 3: gravity, electrical strong force, and electro-weak force. In part 1, we learned that the standard model describes the strong force and the electro-weak force, but gravity is separate. In part 2, we learned about something called string theory that incorporates both gravity and the other forces. String theory defines 11 dimensions of space, and those dimensions are used by all of the forces shown. In the chart, the forces in the standard model fit into dimensions 5 through 11, while gravitational force fits into dimensions 1 through 4. We learned that string theory allows charged elemental matter to oscillate in the shape of a loop of string without losing energy. But charged electrons can't rotate around the nucleus in orbit because they would lose energy and fall into the nucleus. The electrical strong force is still responsible for proton-to-neutron quark binding via gluons. The electro-weak force is still responsible for proton-to-neutron alignment via quark-to-electron binding, and it's also responsible for electron binding via photon exchanges. So what causes radioactivity? What force determines when the nucleus will release alpha, beta, or gamma rays? Well, on Earth, it's not gravity and it's not the electrical strong force. Primarily, it's the electro-weak force that determines the absence of go-to zones, and that's what governs beta decay radioactivity. And the electro-weak force also determines the presence of too many go-to zones, and we've seen that as an enabler of alpha decay radioactivity in light nuclei. Finally, the electro-weak force is also what governs the release of energy in the form of photons, and that's what gamma decay radioactivity consists of: photons exiting the nucleus. And finally, in the credits section for Part 2, we see once again that GUMMI stands for Generalized Understandable Models of Intranuclear Instruction. This means that the GUMMI models are not scientific predictive models. They are not even drawn to scale. The GUMMI models are solely instructional models that graphically introduce many new and novel concepts to the student in an easy-to-grasp format with a series of simple incremental building blocks. The 3D computer models of the lighter nuclei were made with Magic Camera ray trace software. Again, most of the knowledge and all of the references were garnered from the 3 authors listed. Thanks for listening and learning about the GUMMI baryons.